Hello! Welcome to the first video on my channel to cover the area of applied maths known as mechanics. Now, I thought what better way to start exploring a new area of maths than to have a video laying out some good practices and habits to have when approaching this stuff. Therefore, this video is designed to either act as an introduction to this area of maths if you're completely new to it, or as a refresher for those of you doing revision and wanting to boost your performances, because ultimately, in my experience, anybody who's dropping a fair number of marks on this mechanics content is somebody who's probably not doing at least one of the things I'm talking about in today's video. A good starting point would be to first explain what mechanics actually is, and mechanics is the maths that deals with the movement of physical objects and the interactions between them. You'll probably notice a running theme focusing on things such as velocity, forces, and acceleration, and although mechanics progresses on to deal with more than just those three things, it's funny how much of it does end up either directly involving them or things causing or caused by them. I won't dance around the inescapable truth that this stuff does have a big overlap with physics. But it is worth noting that we're going to be approaching it from a maths point of view, and also, although this is physics stuff, the mechanics content we cover in Maths A-level is fairly intuitive. What I mean by that is that this isn't the area of physics focused on what's going on at the molecular level, things that are difficult to visualize. Instead, this is stuff that you can observe in the world around you and that you've naturally picked up an understanding of throughout your normal life. So that actually leads me on to the first bit of advice I want to give you, which is that it's a really good idea to try to visualize and think about logically what you would expect to have happen in the scenario. Because there are a number of times where students will get stuck, and when talking to them, I'll realize they just haven't thought about what would happen if this was actually playing out in front of them. So I'm talking about really obvious things, like for instance, if you got an object on a flat surface and then you start pushing it, well, it's probably going to start moving in the direction you push it in. Or if you have an object on a sloped surface, well, if you just leave it there and there's no other external forces going on, it's probably going to start moving down the slope because of gravity. So it's all these sort of things that kind of just make sense based on what you know happens in the world around you, and if you just stop to think about these things, it can make the situation a lot easier to deal with, rather than overthinking it and thinking about the exact wording of all of the laws of physics that we're going to be teaching you as part of this stuff. A second key bit of advice is that it's really important to extract all the key information from the question. A lot of the questions in mechanics are sometimes actually quite wordy because they're having to describe the scenario in words, but the problem is that means there's a lot of information given to you that does affect what you do with the equations. And so it's really important you do pick out all that information at the beginning rather than just launching straight into the equations themselves. However, some advice as part of that is to not let your eyes just get immediately drawn to where the numbers are. Because although that's very tempting as a maths person to go, ooh, numbers, and just focus on them and start trying to put them into equations, it's worth pointing out in mechanics there are some very key things hidden in particular terms and words that you do need to pay attention to because they completely change how you approach the question. Like for instance, in this one sentence alone, if you're careless, you might miss out the fact this question says decelerate, which is important for whether you have plus signs or minus signs in front of some of the numbers. And then also this word rough, which is also important for whether you include an extra number or not. So it's very easy to miss these things out if you're being careless. Therefore, a good bit of advice I can give you is to go through the words methodically, from left to right, line by line, and reading each bit in turn to decide, is this useful? Is this something that's going to impact the maths? Because if it is, you need to consider it. The problem is, when extracting all this information, you then might not be sure exactly what you're going to do with all of it. Some people like to do what I've just done by highlighting or underlining the key parts of the original wording, but ultimately, that still isn't helping you process the information. So therefore that leads me on to the third bit of advice, which is that it's a really good idea to not just jump straight into making the equations and to draw a diagram first instead. That's really important because a diagram can give you a good overview of what's going on, seeing where things are in relation to each other, and just seeing how the numbers relate to the various objects that are appearing in our particular scenario. I've got an example here for us to look at so we can have a go at getting used to extracting information and then converting it into a useful diagram. It goes without saying that obviously when I get on to actually covering full mechanics topics, you'll get a better overview of me doing this sort of process as part of that anyway, but I thought it was a good idea to give you a taster of how I would approach this sort of thing. The question says we've got 3 points, P, Q and R, that lie on a straight line. Immediately therefore I can stop and I can start to already draw some stuff. I don't need to read any further on to know that I can start adding things to my diagram. Then reading on, it says in that order. That's implying the letters P, Q and R appear in the order P, then Q, then R along that line. So you notice as I'm going along, I'm not even having to get to the end of the sentence to know when I've got enough information to start adding extra things to my diagram and important bits of information like that. Next bit says that P and R are both 16 meters from Q. So that means P to Q is 16 meters. And it also means Q to R is 16 meters. So I can put those measurements on there on my diagram so I can see them. At the beginning, particle A is at P, so therefore I can draw a shape to represent particle A. And I'm going to label it A, like that. Particle B is at R, so let's do another object to represent B. Particle A is travelling at 3.5 meters per second towards Q, so that means A is travelling from P towards Q, so in that direction, and then I can write the 3.5 meters per second there. Although the number was already written in the words, by adding it to the diagram in this way, it makes it more clear what object that number is associated with, as well as pairing it with the direction it's going in, because those are all things that do affect the calculations. Initially, particle B is travelling at 2 meters per second in a direction towards Q, so that means I can put an arrow this direction instead, and putting it as 2 meters per second. And we're also told that it's accelerating at 1 meters per second squared. So that means that's another thing I can add to the diagram. So I'm going to have another arrow and label it with 1 ms to the power of minus 2, because that means meters per second squared. You might notice that I've decided to draw the velocity as arrows that are not connected to the object, are just floating alongside it. And then I've also done an arrow for acceleration, but I've done that as a double arrow. Although these aren't things you're going to be marked on per se, they're all just good ideas to do because it helps separate out the information and makes it clear-cut what each thing is, which is important for then avoiding making silly mistakes when you come to do the calculations. By presenting everything in a certain way and putting everything in a certain place, it helps add a layer of consistency and conformity to some questions that ultimately are very varied. And ultimately, mechanics is a topic that really rewards people who approach it in a methodical and careful manner rather than just launching into it in a slapdash manner, because that's when you miss bits of information or misread it and then you get completely the wrong answer. My fourth bit of advice is to be aware that things happening left and right can be dealt with completely separately to things that happen up and down. This is not a new concept. This is already an idea you've been dealing with a lot when it comes to pure maths and coordinates. What happens with x coordinates is a separate calculation to what goes on with the y coordinates, etc, etc. And so therefore, nothing changes when you get to mechanics as well. If you have an object and there's a lot of different arrows with numbers going on, so we can have an arrow over there with number 2 associated, an arrow over there with number 3 associated. Let's say we've got 4 going up and we've got 7 going down. Ultimately, we can deal with what's going on left and right as one equation, dealing with those two numbers, and we can have a completely separate equation dealing with what's going on with the up and down stuff. And then it only gets a bit weird when you start later on having to deal with things that are going diagonally. But anyway, we can deal with that in the future. For now, just Focus on this idea that things that are going left and right can be treated separately to what's going on up and down. And the fifth bit of advice is it's really important to decide the positive direction. The way of viewing this is it's almost like you're deciding what you're going to call forwards and backwards, because whatever's going forwards will be treated as a positive number, and whatever's going in your backwards direction, decided by you, will end up being represented by a negative number. So let's say we've got this situation here with these two objects and they're travelling in separate directions. We could say they have got particular velocities by giving them certain numbers, but then when it comes to the calculations, we need to know whether these numbers should be treated as positive numbers or negative numbers. So the way you do that is, as I said, you decide a positive direction, and it's a really, really good idea to notate what your positive direction is. That's really important for both your sake so that you can keep track of what you decided and stay consistent to it, but also for the sake of the examiner who's marking your stuff or anybody trying to read your working. They want to know what's going on and what the positive numbers mean, and by notating what your positive direction is, then it makes it clear to them what numbers refer to what. So the way you notate what the positive direction of something is you write a capital R, you write some brackets, and the lazy way after that is just to literally draw an arrow in the direction you're going to call the positive direction, the almost forwards direction, if you will. So for instance, I could choose to make right my positive direction. Because here's the thing, it doesn't really matter which direction you choose as the positive direction when it comes to what you get as your final answer, it's just going to change the way you get there. So if I choose right as my positive direction, that means the velocity of A, in that case, would be positive 8. Whereas the velocity of B, as that's going to the left, and that's my backwards direction, if you will, then therefore the velocity of B would be negative 5 as it's going in the opposite direction. But that's just one option. Did I have to choose right as my positive direction? No. Alternatively, you could do it this way. You could decide that left is your positive direction, and therefore you would draw the capital R, the open brackets, a left pointing arrow, close the brackets, put a colon. The colon's important, by the way, to make it clear that this notation isn't part of the actual calculation, it's just a bit of information. But once you've done that, then that means this time the velocity of A is going in the opposite direction to the positive direction, and so therefore this time it's the velocity of A that's the negative number, and this time it's the velocity of B that's going in the same direction as our positive direction, so therefore the velocity of B will be positive 5. So it's really important that you both consider what the positive direction is, you also notate it, but then you also make sure that you are consistent with it in all your calculations. And so, with all that said, in summary, first of all, try to visualize and think about what's going on, pretending as if this was a physical scenario playing out in front of you. You can use your intuition to work out logically what you would expect to have happen if that was going on. Also remember to extract all the key information from the words. Don't let your eyes just get drawn to the numbers, because there's really important information hiding in the words as well, and you want to go through it in a methodical way to make sure you miss none of the information out. Draw a diagram first. This is a really important step for helping you visualize about where all the objects are in relation to each other, but also helping you start to build a cohesive overall map of what information is related to what object and how it's going to affect the overall question. Remember that different dimensions can be treated separately in separate equations. And then lastly, remember to decide your positive direction and also importantly notate it and stay consistent to it. Okay, that's my introductory advice to mechanics. In future videos, we'll look at actually applying those ideas to help us solve some questions, and also I need to actually explain some mechanics topics, so I'll see you in some of those future videos. Goodbye!